Hey folks, Bill Armstrong here. Thought we'd work through the solutions for practice test 2. The first one, you were given an angle. Let's see. Theta equals 7 pi over 6. And you were asked to find exactly the 6 trig function values for theta. I consider a problem like this to be a basic unit circle problem. The unit circle is quite arguably the most important feature, the most important structure in trigonometry. If you know the unit circle, you're going to know so much of trig. So let me quickly sketch a unit circle. And that's not too bad for me. So here, you're given theta is 7 pi over 6. First thing is we have to know where 7 pi over 6 terminates. 7 pi over 6 is an angle that terminates approximately right here. It's out in quadrant 3. Next, you need to know the coordinates of the point on the unit circle where 7 pi over 6, intersects the unit circle. Coordinates of that point, the x-coordinate is negative square root 3 over 2, and the y-coordinate is 1/2. If you know the x-coordinate is negative square root 3 over 2, and the y-coordinate is negative 1/2, if you know those two, you're going to know the 6 trig function values for theta. You know specifically that the sine of 7 pi over 6 is the y-coordinate, negative 1/2, and the cosine of 7 pi over 6 is the x-coordinate, which is negative square root 3 over 2. If you know those two, the other 4 of the 6 trig functions, the other 4 are free. And that's because you know tangent is simply sine over cosine. That's an old quotient identity. So sine, which is negative 1/2, over cosine, which is negative square root 3 over 2. And you should reduce that down, negative 1/2 over negative square root 3 over 2. That reduces down to 1 over square root 3. Reciprocal of sine is cosecant. So since you know the sine is negative 1/2, you know cosecant is negative 2. Reciprocal of cosine is secant. So you get the secant of 7 pi over 6 is negative square root 2 over 3. And finally, the cotangent of 7 pi over 6, well, that's just the reciprocal of tangent, which gives you square root 3. So the unit circle gives us the 6 trig function values of thetas. Here are the 6 trig function values of 7 pi over 6. And that's what you should have for number 1. All right, number 2, I gave you the function 3 cosine 2x, and in part A, I asked you what is the amplitude of the graph of this function. So in part A, remember that the amplitude is the absolute value of A. A is the number that's in front of cosine here. So here A is 3, and the absolute value of 3 is 3. So for part A, you should have that the amplitude is 3. In part B, I asked you what is the period of the graph. Remember, period is nothing more than the length of an interval in the domain, the x-axis, that we would see one complete cycle of the graph. If you know what it looks like for one complete cycle, then you'll know what it looks like everywhere, which is why we tend to do the graphs just on one period. In any event, period, you should have read, is given by the little formula 2 pi divided by b, where b is that number right there, 2. So a was 3, b is 2, so for this problem, the period is 2 pi over 2, or pi. So the period for this graph would be pi. Now in part C, I asked you to sketch the graph over one period and to label the quarter points. So to sketch the graph over one period and label the quarter points, I know you saw how to do this in the ebook and you've practiced how to do this. I'm going to do a very similar process to what you have read or seen. I might do it slightly differently, but at the end of the day, we're going to have the same graph. So what I do is once I know the period, I know the period is pi, I observe that there's going to be no phase shift at all here. So that means with no phase shift, the left endpoint of one period is x equals 0. The right endpoint of one period is nothing more than that left endpoint plus the period. So since the period was pi, the right endpoint is pi. So to get the other quarter points, I kind of do it without really using a formula or anything. I know that the midpoint here, this quarter point right here, is halfway between 0 and pi. So I'm just finding the average of 0 and pi. And we know how to find an average. Add together, divide by 2. So that gives me the midpoint to be pi over 2. The first quarter point is nothing more than the average of the left endpoint and the midpoint. And again, we know how to find an average. Add those two together and divide by 2, which will give me pi over 4. And the third quarter point, again, it's the halfway point between the midpoint and the right endpoint of the period. So it's simply finding an average. So I take pi over 2 plus pi, add them together, and then divide by 2. And that gives me 3 pi over 4. So these are my 5 quarter points. It's the left endpoint of one period, the first quarter point, midpoint, third quarter point, right endpoint. Since my amplitude was 3, I should scale my y-axis to go up to 3 and to come down to -3, because this graph has absolutely no vertical translation at all. It had no phase shift, no vertical shift. It's going to be a pretty straightforward graph. And then the beauty of these quarter points is if you take those x values and you toss them in to the function where you see x, what you would see is that for each one of these quarter points, when you toss it in here for x, it's going to drop you off at one of those easy points on the unit circle. And what I mean by an easy point is the point where the unit circle it intersects the coordinate axes. For example, you put 0 in here for x. 2 times 0 is 0. Cosine of 0, that's 1. 3 times 1 is 3. So that point is on the graph of this function. Put pi over 4 in here for x. The first thing that happens is it gets multiplied by 2. 2 times pi over 4 is pi over 2. Pi over 2 is up here, the top of the unit circle. The cosine of pi over 2 is 0. 3 times 0 is 0. And likewise, if you put pi over 2 in here for x, 2 times pi over 2 is pi. So that's over here on the unit circle. Cosine of pi is -1. 3 times -1 is -3. And if I continue, I would finally get those points that lie on the graph, and I connect them with the smooth curve, and that is the graph. Make that bigger so I hit it. That is the graph of 3 cosine 2x over 1 period. Amplitude 3, period pi. That's the graph labeling the important points, the quarter points. And that's it for number 2. All right, here in number 3, I gave you the function f of x equals 4 cosine 2x minus pi over 6. Part A, I asked you to determine the amplitude. Part B, the period. And part C, sketch the graph over 1 period, label the quarter points. Very similar directions to what you just saw for number 2. So it should have some stuff that follows very similarly to number 2. In other words, part A, the amplitude is the absolute value of 4, the number we see here. So we get the amplitude to be 4. Part B, the period, is 2 pi over b, where b is 2, so we have the period to be 2 pi over 2, which is pi. So the amplitude is 4, the period is pi. This one will have a phase shift. There's going to be the basic graph of cosine is going to be shifted horizontally to the right or to the left. So the key is, can we find the left endpoint of 1 period, and can we find the right endpoint of 1 period? Because if we can find the left endpoint of 1 period and the right endpoint of 1 period, as we saw in number 2, it's pretty easy to get the midpoint, the first quarter point, and the third quarter point, because all we're doing is finding averages. Here's how I get the left endpoint. And I'm going to abbreviate the left endpoint of 1 period. I'm going to abbreviate that LEP. It's left endpoint of 1 period. Because I know the basic graph of cosine, starts at x equals 0. I'm going to take all this junk I see in the parentheses, 2x minus pi over 6, and I'm just going to set it equal to 0. And I'm going to solve this for x. When I solve it for x, I add pi over 6 to both sides, multiply both sides by 1/2, and I get the left endpoint of 1 period to be pi over 12. And I'm sure that's the same thing you have, but the book may have shown you a slightly different way to get that left endpoint. Either way is fine. Obviously, I wouldn't show you something that's illegal. Once I know the left endpoint, there are really 2 different ways I can find the right endpoint of 1 period. I can, and I abbreviate right endpoint, REP, the right endpoint of 1 period. I can take the junk I see inside the parentheses and set it equal to 2 pi. Why 2 pi? 2 pi because the basic graph of cosine x, which starts at 0, ends at 2 pi. It's the basic period for cosine. This isn't just cosine, it's cosine of some junk. And if I solve this for x, so I'd have to add pi over 6 to both sides. 2 pi, which is 12 pi over 6, plus pi over 6. That's a 13 pi over 6. And then multiply by 1/2. I get the right endpoint of 1 period to be 13 pi over 12. Please note, the right endpoint is exactly the same thing as taking our left endpoint of 1 period, which was pi over 12, and just adding 1 period to it. 1 period. Here the period was pi. So pi over 12 plus pi, 1 period, also gives us the right endpoint of 13 pi over 12. And quite frequently, if I know the left endpoint in the period, that is how I get the right endpoint. I just add one period to the left endpoint. This is all necessary now to sketch the graph. And here's how I go about sketching the graph of one of these beasties. Make my x-axis and my y. And I lay off one period on my x-axis where I know the left endpoint is pi over 12 and my right endpoint is 13 pi over 12. Those are two of the five quarter points, left endpoint and right endpoint. So now I would find the midpoint, because the midpoint is nothing more than the average of those two. Forgot a 1 there. It's just the average of pi over 12 and 13 pi over 12. It's the midpoint. So I add those together, gives me 14 pi over 12. Take half of that, and I get 7 pi over 12. The first quarter point, well, that's the average of the left and the mid. So I add those two together. That gives me 8 pi over 12. Take half of that. So half of 8 pi over 12 is 4 pi over 12. Notice I wrote that as pi over 3. I went ahead and reduced it down. Finally, to get the third quarter point, I would add the mid and the right endpoint together to get 20 pi over 12. I'd take half of 20 pi over 12 to give me 10 pi over 12. And notice that reduces to 5 pi over 6. And amplitude of 4. So my y-axis, I should go up to 4. And down to -4. There's no vertical shifting here, so I should be good just labeling that on my y-axis. And I go through the same process, at least in my head. This is the left endpoint of one period, pi over 12. Notice when pi over 12 comes in here for x, 2 times pi over 12 is pi over 6. Pi over 6 minus pi over 6 is 0. Cosine of 0 is 1. 4 times 1 is 4. As I mentioned in number 2, those quarter points do a wonderful job of dropping us off at the 4 easiest points on the unit circle. When I put pi over 3 in here for x, 2 times pi over 3, well, that's 2 pi over 3, or 4 pi over 6. And 4 pi over 6 minus pi over 6 is 3 pi over 6. 3 pi over 6 reduces to pi over 2. That drops us off at that point right there. What's the cosine of pi over 2? The cosine of pi over 2 is 0. And continuing around, 7 pi over 12, I toss that in. I think we would see -4 comes out. For 5 pi over 6, I think we'd say 0 comes out. And for 13 pi over 12, we get 4. And we get a graph that looks something like that. For number 3. For number 4, I'm going to use the work I've already done. Notice in number 4, I make a little break right here. Number 4, you were asked for f of x equals 4 secant 2x minus pi over 6. You were asked to determine the period. And then in part B, I asked you to sketch the graph over one period and label the vertical asymptotes. The key to doing number 4 is doing number 3. The reason why: secant is the reciprocal of cosine. So to get the graph of 4 secant 2x minus pi over 6, we're going to use the graph of, here in number 3, we're going to use the graph of 4 cosine 2x minus pi over 6 as our guide. Notice for part A in number 4, you're asked what the period is. The period is going to be the same as it was in 3. Part B, the period here was pi, the period here is pi. It's got to have the same period because they're reciprocals. So here's the guide. Here's how we can use the graph of, and let me label this graph. This is the graph of y equals 4 cosine 2x minus pi over 6. Here's how we use the graph of that function as a guide to get the graph of 4 secant 2x minus pi over 6. Wherever this graph has x-intercepts, those will be the vertical asymptotes for the graph of secant, the 4 secant 2x minus pi over 6. So here's an x-intercept, here's an x-intercept. Those are the vertical asymptotes. So here is one piece of the graph of 4 secant 2x minus pi over 6. And now the rest is up to you. What I mean by that, do you want to take the graph that you did in number 3, the graph of 4 cosine 2x minus pi over 6, do you want to extend it to the left to find where the x-intercept is over here? Or do you want to extend it to the right to see where the x-intercept is to the right over here? That's up to you. I don't care which way you go. I don't care if you extend the graph this way or if you extend the graph that way. One thing I would note is that the distance between the x-intercepts on the graph of 4 cosine 2x minus pi over 6, this distance, well, it's the distance from pi over 3 to 5 pi over 6. It's the distance from 2 pi over 6 to 5 pi over 6. That distance is 3 pi over 6. So you either come 3 pi over 6 units this way to find the x-intercept, or you go 3 pi over 6 units that way to find the x-intercept. And yeah, you know what? I'm going to go this way, just for fun. So if I come 3 pi over 6 units this way, 5 pi over 6 plus a 3 pi over 6 is 8 pi over 6. That's 4 pi over 3. That gives me another vertical asymptote. And here is the other piece of the graph of 4 secant 2x minus pi over 6. I wish I had colored chalk here. I would have done the graph of 4 secant 2x minus pi over 6 in a different color. But just to recap, this is the graph we did in number 3. That's the graph of 4 cosine 2x minus pi over 6. We used that graph as a guide to get the graph here in number 4 of 4 secant 2x minus pi over 6. This and this, that's the graph of 4 secant 2x minus pi over 6. Keep in mind you could use that same idea if it were sines and cosecants. In fact, the way to get the graph of a secant or a cosecant is to first graph the cosine or the sine and use it as a guide. So we have number 3 here. Here's the graph for number 3. And number 4. This piece here and this piece up here is the graph for number 4. And I could come in here in case someone doesn't like it. And I can erase that cosine graph. So that all you see is the graph for secant 2x minus pi over 6. So that's it for 3 and 4. All right, hey, here in number 5, I gave you the function f of x equals tangent 2x. Part A, determine the period. And part B, sketch the graph over one period and label the vertical asymptotes. So in part A, here you need to remember that for tangent and cotangent, the period is pi divided by b, where here b is 2, so we have the period to be pi over 2. So hopefully for part A you had the period of that graph to be pi over 2. For part B, to get the graph over one period and label vertical asymptotes, well, folks, I'm going to keep a problem like this pretty basic. If you know the period is pi over 2, I would find the vertical asymptotes that are on either side of the y-axis. And that's because they're mirror images around the y-axis. So all I have to do is take pi over 2 and divide it by 2. Pi over 2 divided by 2 is pi over 4. That gives me, there's a vertical asymptote at pi over 4, and the other vertical asymptote is negative pi over 4. And I'll then just sketch the typical tangent curve. And that's really it for number 5. F of x equals tangent 2x. All right, hey, here in number 6, you're asked to determine the exact value of the following. Well, there's 6 of them I gave you here. So let's look at the first one, 6a. Inverse cosine of square root 3 over 2. I'm not going to rehash the definitions of the inverse trig functions. I'm just going to kind of focus in on, what the purpose of the inverse trig functions are. It's an angle finder. You're really being asked, give me an angle where the cosine of that angle is square root 3 over 2. That's the purpose of inverse cosine. It's finding an angle. And if you look at that definition of inverse cosine, it's finding an angle off of the top half of the unit circle. Yeah, it's coming back to the unit circle again. Find an angle off the top half of the unit circle. I believe you'll see in the definition it has a 0 to pi. Well, 0 to pi is the top half of the unit circle. If you really know that unit circle, then you know the angle on the top half of the unit circle, that when you do the cosine of that angle and it'll give you square root 3 over 2, you know that the answer here then is pi over 6. Because the cosine of pi over 6 is square root 3 over 2. So inverse cosine square root 3 over 2, pi over 6. Part B, I asked you to find the inverse sine of square root 3 over 2. Well, the whole purpose of inverse sine is to find an angle. Here, you're trying to find an angle on the right half of the unit circle. If you look at that definition of inverse sine, it'll have something in there about negative pi over 2 to pi over 2. Well, negative pi over 2 to pi over 2 is the right half of the unit circle. And if you really know your unit circle, you're going to say inverse sine of square root 3 over 2. That's pi over 3. And hopefully you have those two right now. C, part C. Let me try to squeeze C in down here. Inverse sine negative square root 3 over 2. Again, inverse sine is going to find an angle off the right half of the unit circle. And that angle on the right half of the unit circle that we're looking for is the angle about right here. And this is the one area where the inverse trig functions could get just a little tricky. That if you're thinking, oh, I know what that angle is, it's 5 pi over 3. You found the correct location, but you don't have the correct answer. The correct answer here is not 5 pi over 3. It is negative pi over 3. Two reasons why. Reason one, 5 pi over 3 isn't in the interval negative pi over 2 to pi over 2. It's not in that interval. Reason two is if you think you're looking on the right half of the unit circle, if you were to sketch 5 pi over 3, you would be sketching something like that. You came out into an area where it's not defined, which I guess is the same as the first reason. It's not in the interval negative pi over 2 to pi over 2. So make sure for C, inverse sine of negative square root 3 over 2, make sure you have negative pi over 3. Part D, you're asked inverse cosine of negative square root 3 over 2. Well, inverse cosine, you're looking for an angle on the top half of the unit circle. That's from 0 to pi. I believe that angle is over here. And you should have 5 pi over 6. So far, so good, I hope. For E, you're asked to find the inverse tangent of negative 1. I expect you to know pretty quickly, off the top of your head, that inverse tangent of negative 1 is negative pi over 4. Inverse tangent, it too is finding an angle. I mean, that's the job of the inverse trig functions, to find an angle. It too is finding an angle off the right half of the unit circle. It's just almost exactly like inverse sine. The only difference is not at the end point. And that's because tangent, the basic graph of tangent, isn't defined at negative pi over 2 or pi over 2, vertical asymptotes. Besides knowing off the top of your head that inverse tangent of negative 1 is negative pi over 4, I would also expect you to know inverse tangent of inverse tangent of 1 is pi over 4, and inverse tangent of 0 is 0. Then finally, F, you're being asked to find the inverse sine of 2.135. Well, for this one, I need you to recognize this number is larger than 1. Since it's larger than 1, there's no solution. There is no angle that when you do the sine of the angle, it's going to give you a number larger than 1. And final comment on the inverse trig functions. Notice I've mentioned more than once that the job of inverse trig functions is to find an angle. I reviewed on what part of the unit circle it's looking for an angle. But even from the definition of the inverse trig functions, and what I stressed here, our angles given are in radians. You know, it would not be correct for A if you said 30 degrees. That would not be correct. And I don't have it in the directions. You know, my directions here are determine the exact value of the following. You can't put 30 degrees here. You have to put pi over 6. You have to know that the definitions of the inverse trig functions that we are looking for the angle in radians. And that's because a radian is a real number. We're looking for real numbers. And that's pretty much it. So I hope that's what you had for number 6. Hey folks, number 7 says determine the exact value of the following. I have 4 more here. The first one was sine of inverse sine of 1/2. Well, if you know this, the sine and inverse sine, they kind of undo each other because they're inverse functions. You could almost immediately say that the answer here is 1/2. And it is 1/2. But if you take it a step at a time, and you say, all right, well, what's the inverse sine of 1/2? You should get the inverse sine of 1/2 is pi over 6. Inverse sine of 1/2 is pi over 6. What's the sine of pi over 6? It's 1/2. So, pretty straightforward, pretty friendly one. For B, well, not quite as straightforward, but still friendly. What's the cosine of the inverse sine of 1/2? Well, you just take it a step at a time. What's the inverse sine of 1/2? Inverse sine of 1/2 is pi over 6. Well, we just did that up here. Now, what's the cosine of pi over 6? That's square root 3 over 2. And I should point out, I'm getting these things kind of quickly, not because I've done this for too many years of my life, but because I know the unit circle. It all comes back to that unit circle. C. So part C, you are asked to find the inverse cosine of the sine of pi over 3. Take it a step at a time. Sine of pi over 3. Well, the sine of pi over 3 is square root 3 over 2. Now the inverse cosine of square root 3 over 2 is pi over 6. So for part C, you should have inverse cosine of sine pi over 3 is pi over 6. And then finally part D, it's kind of a mirror image of what part A was. You're asked what's the inverse cosine of cosine pi over 6. Knowing that inverse cosine and cosine are inverse functions of each other, you'd think they undo each other, and we should end up with pi over 6. But just to verify that we do, we could take it a step at a time. Cosine of pi over 6, well, that's square root 3 over 2. Inverse cosine of square root 3 over 2, that is pi over 6. And again, let me just mention one more time how I'm quickly determining these values from my knowledge of the unit circle. Knowing where those special angles terminate on the unit circle, knowing the coordinates of those points on the unit circle, and knowing the x-coordinate is cosine and the y-coordinate is sine. Knowing that can go so far in trig. And it's going to be with you next week when you start new material after this test. Okay, that's number 7. Hope you had everything here. All right, hey, here on number 8, I ask you to determine the exact value of cosine of inverse sine square root 5 over 9. Here's how I look at one of these problems. And I think most of you are going to be calculus bound, and I can't impress upon you enough how important the basics of trig are in calculus. When I say basics of trig, I'm talking unit circle and identities. So I'm going to attack this in a way that's going to review a lot of these things that's going to be important when you take calculus. First off, I look at this stuff here, inverse sine square root 5 over 9. And that isn't something that I really know off the top of my head on the unit circle. If this were inverse sine square root 3 over 2, or as we saw in number 7, part B, if this were inverse sine of 1/2, this is a pretty easy problem. But I don't know off the top of my head what inverse sine square root 5 over 9 is. But I do know that it represents an angle on the right half of the unit circle. So the first thing I do is I write down, I know that's an angle. Let me call that angle theta. So this is representing some angle theta, and I know it's on the right half of the unit circle because that's my definition of inverse sine. It's finding an angle from negative pi over 2 to pi over 2. By just writing this down, I have turned our original problem into nothing more than finding the cosine of theta. And at this point you're saying, well, yeah, that's true, but you don't know what theta is. You know, big deal. This equation, theta equals inverse sine of square root 5 over 9, it really means that sine of theta is equal to the square root 5 over 9. If this equation's telling me I'm looking for an angle on the right half of the unit circle, this equation is now telling me that that angle I'm looking for, which is on the right half of the unit circle, it has to definitely be out here in quadrant 1. Because sine is positive in quadrant 1. Sine is not positive in quadrant 4. So I think I could use this, and I'm going to review an identity now, Pythagorean identity, that because I know sine is square root 5 over 9, and I want to determine cosine, I could use the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. Cosine squared theta plus, I'll toss that in to my identity for the sine of theta. When I take square root 5 over 9 and square it, I'll get 25 over 81. I'm sorry, 5 over 81. And then when I subtract 5 over 81 from both sides, I get 76 over 81. And then when I take the square root of both sides, I get cosine theta equals plus or minus the square root of 76 over 9. But my answer is that the cosine of theta, my answer here is the positive one, square root 676 over 9. How do I know to use the positive one and not the negative one? Because this equation told me theta is in quadrant 1. And I know cosine's positive in quadrant 1. So that's how I come up with the exact value of cosine theta. And hopefully you got the same thing. That's it for number 8. All right, finally here's number 9, verifying an identity. Here I asked you to verify the identity 1 minus cosine x over sine x plus sine x over 1 minus cosine x is equal to 2 cosecant x. Here's how I verify identities. I start off, I make a vertical line. I drop it down from my equal sign. And I pick one side of the equation to do all my work on. And I try to get it to match the other side of the equation. Preferably, you pick the more difficult side of the equation to do your work on. So when I look at this one, to me, I don't think there's really much debate. The left side of the equation does look more difficult than the right side. I mean, heck, the right side is just a little 2 cosecant x. You have all this junk happening over here on the left side. So I'm going to pick the left side to do all my work on and see what we can come up with. Here's how I begin on the left side. I have 2 fractions. So why don't I find a common denominator and then turn it into 1 fraction once I get a common denominator. The common denominator is sine x times 1 minus cosine x. So I would have a 1 minus cosine x times 1 minus cosine x over sine x times 1 minus cosine x plus sine x times a sine x over a sine x times 1 minus cosine x. That's just rewriting each fraction with the common denominator sine x times 1 minus cosine x. Next, since we have a common denominator, why don't we go ahead and make it into 1 fraction. And at the same time, I'm going to do another step. As I'm making this into 1 fraction with the denominator of sine x, 1 minus cosine x, I'm going to go ahead and do a little foiling here, taking the 1 minus cosine x times the 1 minus cosine x to get a 1 minus a 2 cosine x plus a cosine squared x plus, and then sine x times sine x is a sine squared x. And that's all over the sine x times a 1 minus cosine x. So I've taken the ugliness and I've turned it into 1 fraction. It's like, well, now where do I go next? Well, look what's jumping out at us. Something we just saw in number 8. Here's a cosine squared x plus a sine squared x. Cosine squared x plus sine squared x, and that's 1. So for the cosine squared plus sine squared, I'll replace that with a 1. And then with this one, I have a 1 plus a 1. My numerator turns into 2 minus 2 cosine x. And then look up here in the numerator, I can factor out a 2. And once I factor out the 2, I can cancel out the 1 minus cosine x over the 1 minus cosine x. They cancel out, which leaves me with 2 over sine x. And 2 over sine x, well, that's nothing more than 2 cosecant x. I've done all of my work on the left side, and I finally matched the right side. So at this point, I'm done. I have verified the identity. And that was number 9. That was the final one on the practice test. Hopefully you're feeling pretty comfortable for this test. Hopefully you got most things correct here. Common question is, are there more ways to verify an identity than the way I've just shown? Generally speaking, yes, there are. Doesn't mean my way is the only way or my way was the best way. It's just the way I did it. But again, hopefully everything is going smoothly and you're going to go in and do a good job on test 2. So that's it, and thanks for watching.